Hi again. Um, Again, many thanks for inviting me to contribute to the workshop. In particular, thanks to Professors Upadhyay and Gupta for arranging this. I very much appreciate it. So this is my second lecture on this topic, the concept of statistical evidence that is basically coming from a paper that I wrote and has been published in the journal Encyclopedia. It's a review paper about the concept of statistical evidence. And the first lecture was really about the various attempts that have been made so far, not so far, but various attempts that have been made to define the concepts of statistical evidence that are non-Bayesian. And today I want to talk about the Bayesian approach to defining evidence. And I think this is a very powerful argument as to why one might want to be a Bayesian, because it becomes very easy to do this in the Bayesian context. It's actually a little bit strange to me that this hasn't been done before to a great degree. Okay. Okay. So just to remember, we have the following. Our interest is in. We have a statistical model, right? I've called these things inference spaces. And for the Bayesian problem, the inference space is composed of a prior, a sampling model, and the data X. Those are the ingredients that we're going to use to apply principles to derive inferences. About some quantity of interest we'll call psi, little psi. It's a function, can be expressed as a function of the model parameter. Big psi function is the function of the model parameter theta. And when we're interested in psi, one of the nice things about Bayesian inference is that we can integrate out what we call the nuisance parameters. The nuisance parameters are all those aspects of theta that have nothing to do with the value of psi, right? So theta, big psi will be uh, will be map various number of different values of theta to the same value of little psi. And so we can just integrate out what we call the nuisance parameters, right? So we replace this inference space by the inference space for psi, which is given by the marginal prior for psi. The sampling model I get for the data simply by integrating out the nuisance parameters, and of course, the same data x. So this m is a density function, and it's obtained via this integral here. So this pi d theta psi, given psi is the conditional prior distribution of theta, given that psi of theta is equal to little psi. Now recall the goals of an evidential theory of inference. There are two, really. There's the estimation problem. Based on the data, we want to provide an estimate of psi together with an assessment of its accuracy. Okay, it's not enough just to say we want to estimate psi. We want to say something, we want to estimate it, of course, but you also have to say something about how accurate you believe your estimate to be. Without that measure of accuracy, an estimate is pretty much worthless. And for hypothesis assessment, we want to quote the evidence in favor of or against some specified value psi naught of psi together with an assessment of the strength of evidence. And you notice I put in an emphasis here in favor of and also with an assessment of the strength of the evidence, because I think the previous methods that we've talked about for characterizing evidence didn't really satisfy that, right? They didn't tell us how to get evidence in favor of something being true. Well, the pure likelihood approach certainly understood that, and they did at least try to address it. But again, that approach doesn't really also deal with the assessment of the strength, even though words to that effect were used. Now, the Bayesian approach, this requires some principles. Okay, so what we have to start out with, those ingredients, they specify a joint probability model for psi and x, right? We just take the conditional for the x given psi and multiply by the prior for psi, and we have a joint probability model for psi and x. In fact, this is characteristic of Bayesian inference. Really, Bayesian inference is part of probability theory, right? We're always dealing with probability models. So what we want to add to probability theory are principles that tell us how to make inference, because probability theory doesn't really tell us that. Now, there are two, excuse me, really basic principles. Uh, I call the principle of conditional probability and the principle of evidence. And so let's imagine we have a probability model, which is a triple, right? Is the sample space omega, the sigma algebra script F, and P is a probability measure defined on script F. And we're concerned with the truth of an event A. We don't know whether A is true or false. We've tossed a coin, we've rolled a die, a card has been dealt from a deck of cards face down. We want to know whether the event A is true. Is the card that was dealt face down an ace? Now, well, let's suppose it's two cards, and we want to know whether both cards are aces. So there's a probability of that, right? That's our initial probability, which I'll denote by P of A. And then we're given some information. Somebody says to us, well, I've seen one of the cards, one of them's an ace. And of course, that changes our probabilities. For example, if somebody had said one of the cards is a king, then we know they can't both be aces, and the probability of A is zero. Our belief is now zero, right? So there's a principle of conditional probability, and that says if we start out with the initial belief that A is true as given by P of A, that's what probability does. It measures our belief that some events are true. And after I observe that I've been told or I observe that C is true, then I replace P of A by P of A given C. There's nothing really mathematically that forces us to do that. We just believe that that's the right thing to do. And there are mathematical results that support that result, no doubt about it. But it is an axiom or a principle, if you like, of inference, not just of probability theory. It tells us how to change our beliefs. Now, with that, we can characterize statistical evidence. We can characterize evidence. It's a very simple principle. I call it the principle of evidence. I don't think I'm the first person to use this terminology, but I might be. I don't know. But it's certainly very natural. And it says this: if there's evidence in favor of A being true, if the new probability of A, the probability after I've conditioned on this information that I've been given, is greater than the initial probability, because this information has caused our belief to go up. So that suggests that that observation that C is true is evidence in favor of A being true. And also, if the probability went down, then the information that C is true is contradicting the truth of A, because our belief now has decreased. And there's no evidence either way if the probabilities are equal, right? A and C are statistically independent in this context. So it makes sense that there's no evidence one way or the other. I suggest that this is a highly intuitive and simple characterization of statistical evidence. It's not new to me. Okay, it's been around a long time. The philosophy of science, they talk about this quite a bit in that literature. It's called confirmation theory. And it has a long history there. Here's a quote from a very famous book in the philosophy of science, Popper's 1968 book, The Logic of Scientific Discovery. He says, if we were asked to give a criterion of the fact that the evidence Y supports or corroborates a statement X, the most obvious reply is that Y increases the probability of X. There are many other instances of this. It's been around a long time. Somehow, it hasn't really permeated to any great degree into statistics, although to a certain amount. I'll mention something about that in a minute. Now, the problem with the discussion in the philosophy of science literature, from my perspective at least, is that it's not really statistical. The philosophers are interested in some sort of general theory of induction. What I'm interested in is a general theory of statistical induction. So they come up with all kinds of what they consider to be counterexamples to this confirmation theory. And in fact, Popper did not believe in it. Okay. And here's an example. It's called the paradox of the raven. And the hypothesis is that all ravens are black. We call them crows in Canada, but in other countries they call them ravens. Uh, Now that's equivalent logically to the statement that all non-black objects are not ravens, right? So if all ravens are black, anything that isn't black is not a raven. So if one is true, the other is true. If one is false, the other is false. Now you randomly observe an object and it's not black and not a raven. So that's evidence in favor of the hypothesis that all ravens are black. For example, you see my yellow shirt. It's obviously not a raven. That confirms the hypothesis that all ravens are black. And that seems absurd. Why should that be true? Why should that happen? Why should seeing my yellow shirt confirm the hypothesis that all ravens are black? Well, it turns out if one casts this in a statistical framework, one can explain this. And in fact, I will give the key to explaining this later when I talk about something called the Jeffreys-Lindley paradox. It's the same answer, okay? And in fact, if you want to read about that, you can read about this in my book on measuring statistical evidence on page 132. Well, I cast this problem in a statistical context, and you can see, indeed, seeing my yellow shirt would be evidence that all ravens are black. But, okay, so I'll wait till we talk about Jeffreys-Lindley paradox to indicate what the but is about. Okay, we also have to be concerned with measuring the strength of evidence. There's no point to say there's evidence in favor of something being true or evidence against something being true without saying something about how strong that evidence is, right? So how do we measure that? This turns out to be a rather large issue for Bayesian inference because there is a measure of evidence that has been used for a long time, the Bayes factor. But the strength of that evidence, in my opinion, is not measured properly. And what I say is that the strength of evidence, the evidence says one thing or another, says there's evidence in favor, there's evidence against. We measure the strength of that evidence by how strongly we believe in what the evidence says. And of course, if we're measuring belief now, the principle of conditional probability says all our beliefs are a posteriori, right? So if we get evidence in favor, namely the conditional probability of A given C is bigger than the probability of A, and that probability, conditional probability is big, then there's strong evidence that A is true because we believe what the evidence is saying. If it's small, then we only have weak evidence. Okay, if P of A given C is small, we only have weak evidence. If we have evidence against, namely the conditional probability is less than the initial probability, and P of A given C is small, then there's strong evidence that A is false because that's telling us we believe that the probability of A complement is A complement is true, but not that we believe that A is true, right? So in a very natural way, these posterior probabilities are telling us about the strength of the evidence. So when it comes time to measure the strength of evidence, we do that via posterior probabilities. Now, we also need a numerical measure of evidence. In statistical problems, we need to order, get a set of alternative values for the, in the estimation problem for psi. We need to order those. Which ones are there more evidence for than others, etc. And there's different ways you can do this. The way I'm going to do it, and I think it's probably the most natural way, I put the natural in quotes because maybe there are others, is to look at the ratio. So I take the ratio of the conditional probability to the unconditional probability, and there's an immediate cutoff. I call that the relative belief ratio. And if the relative belief ratio is bigger than 1, then I've got evidence in favor. If it's less than 1, there's evidence against. And notice, the cutoff here is clear. There's no argument about that. That comes from the principle of evidence. And as I said, there are other ways of ordering alternatives. You don't have to use the relative belief ratio, but any valid measure of statistical evidence, which the relative belief ratio is, has got to have a cutoff like that. It has to obey the principle of evidence with a cutoff. For example, I could use the logarithm of relative belief ratio, And that would be a valid measure of evidence with cutoff 0. And in fact, as it turns out, since I'm going to base all my inferences on the relative belief ratio, if I can take any monotone increasing function of the relative belief ratio, all my inferences will be the same. Nothing changes. So in some context, it's worthwhile computationally to look at the log relative belief ratio rather than the relative belief ratio, but it makes no material difference, no difference at all to the actual conclusions that we draw. Now, this relative belief, what I call the relative belief ratio, has been considered before. It's hard to find it because it's a very difficult book to read, but in Keynes' book, Maynard Keynes, the famous economist, he wrote a book called The Treatise on Probability in the 1920s, and he called what I'm calling the relative belief ratio the coefficient of influence. And I think I.J. Good called it a measure of association or something like that. So it has been around a while. It's not due to me, this ratio, right? But it has some very nice properties that I'll mention and why we want to consider the relative belief ratio. In particular, there's another one you probably think right away, well, why isn't he using the Bayes factor? It is a valid measure of evidence. You can show that with the cutoff 1. Okay, and that's due to Jeffreys, I think even in the 1920s, but you can read about it. Probably, I found the best source in his trying to read the earlier papers I found very difficult, but his book, Theory of Probability in 1961, there's a nice section on it. And what is the Bayes factor? Well, the Bayes factor is the ratio of the posterior odds that A is true, which is just the ratio, the posterior odds that A is true is the ratio of the posterior probability of A to the posterior probability of the complement of A, and divide that by the prior odds that A is true. And if this is bigger than 1, it follows from the principle of evidence. It's a valid measure of evidence. It obeys the principle of evidence. And when the Bayes factor is bigger than 1, you have evidence in favor. When the Bayes factor is less than 1, you have evidence against. So why not use the Bayes factor instead of the relative belief ratio? Well, there's a lot of reasons for that, actually. And with a couple of co-authors, we've addressed that in a paper that you can find on my website. How to measure evidence and its strength, Bayes factors, or relative belief ratios. And I'll mention some of the reasons here, but there are a number of others that I'm not going to discuss in this talk because it's not what the talk's about specifically. But anyway, one very simple one is that we can get the Bayes factor from the relative belief ratio fairly easily. It's just the ratio of the relative belief ratio of A to the relative belief ratio of its complement. That is equal to the Bayes factor. And that's obvious from this formula, by the way. And that has an implication, by the way. I think it was I.J. Good who he knew about what I'm calling the relative belief ratio, and he favored the Bayes factor because he noted the Bayes factor, when there's evidence in favor, the Bayes factor is always bigger than the relative belief ratio. But that follows immediately from this formula because if RBA given C is bigger than 1, RBA, if there's evidence in favor of A, there's evidence against A complement. So I'm dividing by a number less than 1 here, which pushes up the Bayes factor. And similarly, if this is less than 1, then this is bigger than 1. And when there's evidence against, the Bayes factor will always be smaller. This is not a good argument for the Bayes factor over the relative belief ratio, and I'll demonstrate why later, in a few minutes, in fact. Now, what about for problems where there are events that have prior probability 0? How do I define the relative belief ratio in that case? Well, I'm going to define it via a limit, which I think is the natural way to do it, right? I think of a sequence of sets. Think of these as balls of radius epsilon centered at psi. And I want to define the relative belief ratio at psi. And I want these balls, as the radius goes to 0, converge what is called nicely. What do we mean by nicely? Well, you could also think of taking rectangles. And for rectangles to converge nicely, all the sides of the rectangle have to converge to 0 at the same rate. If you allow some to go faster to 0 than others, then you won't get the right answer. Okay, they all have to be going at the same rate. This is expressed, the precise definition of nicely can be found in Rudin's book, Real and Complex Analysis. Right? And what happens? The relative belief ratio, I define it to be to calculate the relative belief ratio of one of these neighborhoods. and let epsilon go to 0. And what does it converge to? Well, under very weak conditions, for example, the prior at psi has to be positive and continuous at psi. This ratio converges to the ratio of the posterior density to prior density. Now, what if you did the same thing with the Bayes factor? You get the relative belief ratio. So in a certain sense, the relative belief ratio is the limiting Bayes factor, is the Bayes factor in the continuous case. Why is this right? Well, what is relative belief expressing? It's expressing amount of belief, posterior belief, relative to prior belief, right? And so what this ratio, that's exactly what this ratio is expressing, right? It's the density of psi relative to pi, to the prior. It's the posterior density of psi relative to the prior density of psi. It's expressing our relative beliefs. This is why I call it relative belief. Whoops, I went too fast there. Or did I? Yes. Oh, I'm sorry about that. I got a little mixed up where I am. Okay, so let's talk now about relative belief inferences, and we'll start off with a hypothesis assessment problem. Well, right away, we've got our measure of evidence. We want to assess the hypothesis that the true value of psi is psi naught. Immediately, we have the relative belief ratio. If it's bigger than 1, we got evidence in favor. If it's less than 1, we got evidence against, right? And then we want to measure the strength of that evidence. Well, we've got the posterior probability of psi naught. Now, in certain problems, continuous problems, for example, that probability is going to be 0, right? Or very small, even in discrete problems, it could be very small. So another way to measure the strength of evidence is to compute this like a tail probability here. We calculate what's the posterior probability. How strongly do we believe? What's our belief that the true value of psi has a relative belief ratio that is no greater than the hypothesized value? That's what this probability is computing. So if we have evidence, if the relative belief ratio is bigger than 1 and we have evidence in favor, and this probability is big, that tells us our belief that the true value has an even bigger relative belief ratio is small, so that's strong evidence in favor of the null hypothesis. If you got evidence against, so this is less than 1, and this probability is small, that tells us we have a strong belief that the true value has an even bigger relative belief ratio, and we have strong evidence against. So this works pretty well. There's a caveat to that, and I'm going to talk about that now. When we talked about lecture 1, I noted that there's typically a distance measure and a delta. I called it the meaningful difference, greater than 0, such that when two values are different than delta, the difference isn't practically meaningful. For example, if I'm measuring a length and I'm measuring length to the nearest centimeter, well, delta would be half a centimeter. We don't think of two values as differing if they differ by less than half a centimeter, at least as far as our experiment goes, because we're only measuring to the nearest centimeter, right? Differences that are less than a half centimeter don't count, right? And so if I measure to the nearest millimeter, then differences that are less than a half a millimeter wouldn't count either. So what happens in when we take this measurement accuracy into account, there's typically a grid of values. There's different ways you could do this, but this is how I'm going to talk about it here. There's a grid of values, and one of those, so think of these as being centimeters, psi naught centimeters plus k centimeter, k half centimeters, I guess, where k is an integer, right? And one of these represents the true value as far as our experiment goes. I mean, think of a physicist. Physicist wants to measure the half-life of a neutron. Well, they design their equipment to measure it to a certain accuracy. And no matter what they do, they're not going to get it to greater accuracy than beyond the limitations of the equipment they've designed for the experiment. So we get a partition of the real line into subintervals, where each subinterval is of length delta and has a unique grid point at its center. And there's a reason why I'm doing this, and it has to do with the defect in the p-value. that if I don't do this, I just treat this as a continuous quantity, and the null hypothesis is true, you end up with a uniform distribution. Now, when you take this delta into account, which is what we saw, it was difficult to do with the p-value back in lecture 1, but it's easy to do it here. So the real hypothesis is, null hypothesis is that the true value is in this interval. And so we can calculate the relative belief ratio of that interval. And we can compute the strength by looking at the relative belief ratios of all these subintervals in that partition, right? And so we're making a comparison, if you like, amongst like objects, because each of those intervals is of the same length. And what this guarantees is that the relative belief ratio converges to the maximum possible value, and the strength measure goes to 1 as the amount of data increases. So we get away from this, because the posterior, when the null hypothesis is true, the posterior is going to concentrate completely in this interval, right? Even if it's not equal to psi naught, if it's some value in there, inevitably the posterior is going, for a large enough data set, it's going to be concentrated inside this interval. And so, and by the way, I guess I'm doing it for a real valued psi here, but similar considerations can be carried out for multidimensional psis as well. The strength does the right thing. It converges to 1 when the null hypothesis is true as we increase the amount of data. And you have to do this discretization for that. In fact, this is not a problem because it actually makes your computations somewhat simpler rather than harder. Now here I want to make a comparison with the Bayes factor and what is done and currently done in the literature. And it is currently done because I've refereed several papers where people quote Jeffrey's scale. They compute the Bayes factor, and I'll explain how they compute it in a minute. That's another issue, right, in the continuous case. But let's just suppose everything is discrete for the moment. And I'm going to do an example which shows that this does not work in the discrete case either. And they quote this is evidence in favor, right? If you get a value between 1 and the square root of 10, that's barely worth mentioning. It's evidence in favor, but barely worth mentioning. If it's from the square root of 10 to 10, it's substantial. If it's from 10 to the 3/2, it's strong. Concentrate on this one. If it's bigger than 100, the Bayes factor, you have decisive evidence in favor of the null hypothesis. That is what Jeffreys has said. People have modified this scale to a certain degree, but not by much. They always quote this scale. And if you want for evidence against, just flip them all over with the same, but reverse the order, right? No, the order stays the same, right? The decisive evidence against if it's less than 1 over 10 squared. This scale is not correct, in my opinion. Okay, and I'll show you why. If you can find simple examples that show that something is wrong, something's wrong. Okay, so let's look at an example. This is called the prosecutor's fallacy. It's been around in the literature for quite some time. And not because of how I'm going to use it. It's about as simple as you can get because there's 2 possibilities here, right? And I like it. And it often shows that something that we're commonly doing in statistics does not work properly. So it's an important example, in my opinion. So we have a uniform distribution on a population of size cap n. And a crime has been committed, and a trait was left at the crime scene. And it's shared by m members of the population, where m is much smaller than n. And then I put randomly in quotes because that's not what actually happened in the application. But anyway, a selected individual is found to possess the trait. And then the prosecutor, and this is why it's called the prosecutor fallacy, was actually quoting the probability the person has the trait given they're guilty, which is, of course, 1, because the guilty person left the trait, the evidence of the trait at the crime scene, as evidence of guilt. And people have pointed out, well, really, in this case, the probability of guilt, given that they had what you want, you flip the antecedent and the consequence, right, is the probability of guilt given the trait that they have the trait, and that's 1 over m. If m is 1, yes. But if m is 2, then it's 50-50, right? And if m is bigger than that, it's going down, the probability of guilt. Now let's look at the Bayes factor. The Bayes factor in this case is the value n minus 1 over m minus 1. Remember, that's always bigger than the relative belief ratio, which is, in this case, n over m. Easy to figure out. And that's hugely, if m is much smaller than n, this is huge. So for example, if I take n to be 100,000, m to be 100, the Bayes factor is 1010.1. And so according to Jeffrey's scale, I have, decisive evidence in favor of guilt. Okay? The relative belief ratio is equal to 1,000. So again, that seems, ooh, the relative belief ratio is quite large. I've increased my belief in guilt by a factor of 1,000 over the prior probability, right? But how strongly do we believe the evidence? The probability that the person is guilty, given they have the trait, is only 1 over 100, which is 0.01. And what does that tell us? Well, there's 99 other people out there who could have been the perpetrator of the crime. So it's extremely weak evidence in favor. So this completely contradicts Jeffrey's scale. And, well, you think it through for yourself. I'm convinced Jeffrey's scale is not correct. And we shouldn't convict the person based on that. And this example shows several things. First of all, it shows Jeffrey's scale is not correct. And secondly, it shows that posterior probabilities do not measure evidence. I find this in the literature from time to time. People are trying to use posterior probabilities to measure evidence. They do not measure evidence. Probabilities measure belief. They don't measure evidence. Evidence is measured by change in belief, because that's what the data does. It changes our beliefs, right? And here's another application of this example. I apply it to the hypothesis of innocence. And you calculate alpha and beta for this. Well, this is Birnbaum's confidence comp set. If you look back in lecture 1, they're both equal to alpha is equal to 0.01 and beta is equal to 0. So these are both very small, which means, according to Birnbaum, very strong evidence against innocence. So that's pointing to the right thing. But there is not strong evidence against evidence here, okay? So it's not doing the right thing. It's weak evidence against innocence because it's weak evidence in favor of guilt, okay? So Birnbaum's proposal does not work. And as I mentioned that in the lecture 1, the CLS statistic is being used in practical applications in particle physics. Anyway, this isn't the only problem with the Bayes factor. So I'm really trying to emphasize here, I don't think the current usage of the Bayes factor in the literature is quite right. We want to be doing something else. So what happens when the probability of the null hypothesis, the probability of the set of theta values that lead to the value of psi naught, is 0? Well, what is recommended there, and this goes back to Jeffrey's, is to modify the prior. Use a mixture prior. Put a discrete mass at the point, this set, discrete mass on this set, at this set, right? And then put a prior pi psi naught on the theta values within that set. And take a mixture. So you mix it with the prior that gives you this probability 0. So you have a continuous prior over the sample space, and this is a set of prior probability 0. You put discrete mass at this set, and then you have a prior within that set, a conditional prior within that set, and then you take the mixture of the two of them. And so, indeed, you can calculate the Bayes factor now. But notice, every time I have a different psi naught, I have to use a different prior probability distribution. That in itself is a little bit disconcerting, particularly if I wanted to use the Bayes factor for estimation. How do I do that? It's not so clear. Do I take a different mixture for every different psi naught value so that I can, or psi value so that I can estimate psi? And often people take p equal to a half, by the way. Anyway, using this mixture of the Bayes factor is indeed defined. But now, if you take a density function Like let's take the normal 0, 1 density function, and I change its value at 0. Let's suppose I make the value at 0 equal to 1,000 of the normal 0, 1 density function. Well, that's still a density function. If I do the integration, I'll get all the same probabilities. But is that a density now? No, because density is probability. Probability density is probability per unit volume. We have to define it via a limit. And when you take the limit, you're not going to get 1,000. You're going to get the usual value for the normal density function at 0. It's wrong to think you can just arbitrarily change things on a set of measure 0, and that doesn't make any difference. And then that carries over to conditional probabilities as well. So if I take this probability measure pi, which is, where is it? Oops, the mixture here, pi, which is on the whole parameter space, but I took out a set of measure 0. Well, if I take a limit, the probabilities are still the same on that set as given by pi. And in fact, the conditional probabilities are defined, and you define them by limits. And when you do that, you get, as the limit, the conditional probability you would get by taking pi and conditioning it to that set as a limit. That takes there's a few regularity conditions here, but they're weak, right? So if what happens here, and I've denoted, well, no, if this limiting conditional probability distribution is not equal to the prior probability distribution that you put on this set when you did this mixture, there's a contradiction. There's the conditional beliefs that are induced by the prior pi, and there are the beliefs that you've assigned via the prior pi sub psi naught. That's not good. We don't want any contradictions like that in our theory of statistical reasoning, right? So I would say there's no choice. You have to take this pi psi naught to be this conditional probability distribution. I forgot the dot there. And then when you do that, guess what? And you go through the usual calculation of the base factor with the mixture pair, you get the relative belief ratio. But the prior is still this mixture prior, and that's not necessary. There's no need for the mixture prior approach. No need for it at all. Just define the base factor to be a limit, as I've done, and avoid contradictions like this in your approach. And you've got a better measure of evidence than the current usage of the base factor. I just would not use the mixture prior approach to define base factors. I do not believe it's correct. Okay, so now to inference. What's the relative belief for estimation problem, right? I did hypothesis testing now for estimation. Guess what we're on? Yep. Well, the natural thing is to take the value which has the most evidence in its favor. So I maximize the relative belief ratio. And it turns out you can prove that's always, the relative belief ratio at this estimate is always bigger than 1. Okay. And then I want to say, how accurate is it? Well, I'm going to look at this, what I call the plausible region. It's the set of all those values which have evidence in their favor. Okay? I'm not going to include values that have evidence against them. That contradicts the whole idea here would contradict the whole idea of letting the evidence in the data dictate what we believe to be true. And I'm going to look at the size of that. There's different ways to measure size. It could be volume. In the discrete case, it could be just counting the number of elements in the set. Or it could be take the prior content of that. That's also a measure of psi. But anyway, how strongly do I believe? So I look at the size of this, but also I want to know, how strongly do I believe that the true value is in that set? Well, that's measured by the posterior content of that set, of the plausible region. And an interesting thing here is that this plausible region is completely independent of using the relative belief ratio. It only depends on the principle of evidence. So if I use any other valid measure of evidence, a valid measure of evidence is a measure of evidence that satisfies the principle of evidence, I would get the same plausible region. So for example, so I don't have to take the relative belief estimate. I could use some other rule. For example, I could use the base factor, say I'm in a discrete case. And I could maximize the base, so I don't need this mixture prior for the discrete case business. I could just maximize the base factor, and I will get a value that's in the plausible region. Why not? Is one better than the other? No. Why not? Because they have the same measure of accuracy, the plausible region, the size of the plausible region. That's what's telling us how accurate our estimate is. So any rule that always produced a value inside the plausible region is a valid estimation technique. And one is not better than the other, although there might be criteria that one satisfies that the other doesn't satisfy. Um, More on that in another talk. Now, one thing to know is that the relative belief ratio is, relative belief estimate is the MLE from the integrated likelihood. And the plausible region is an integrated likelihood region. So if there are no nuisance parameters, the MLE is the relative belief for theta. The MLE is the relative belief estimate. And the plausible region is a likelihood region for the theta, right? So there's this nice connection between relative belief theory and likelihood theory. And I think that is a very positive thing. Others have queried that and said, well, it's not Bayesian. Well, I disagree with them on that. I think that is a very good attribute of relative belief theory, that it connects likelihood theory, which has served statistics, I think, quite well, and Bayesian statistics, right? Now, like likelihood, all relative belief inferences are fully invariant under reparameterizations. That's not true of other inference methodologies. In my talk on in the conference, I'm going to talk about decision theory there and things like map, estimator, using posterior means. These are not invariant. And what I mean by invariant, suppose I take a one-to-one smooth transformation of psi, cap lambda, and I have a new parameter lambda, and I calculate the relative belief estimate for lambda. I can just take the relative belief estimate for psi and apply big lambda to it, and I get the estimate for the relative belief estimate for lambda. And similarly, the plausible region for lambda is just lambda of the plausible region for psi. That's a very natural and nice property that you would want any inference procedure to possess. In particular, it allows you to do your computations in any parameterization that you want, and then you just transform to the parameterization of interest. Now, you could also quote a gamma relative belief or relative belief credible region. What you do for that is just like with a likelihood region, you find, or HPD region, you find a constant such that the posterior probability of psi being a value who gives a relative belief ratio greater than or equal to that constant is at least equal to gamma, right? Now, one caveat here is that you have to have the gamma is less than or equal. If you're going to report such a credible region, you could, like a 95% credible region, you could, but one caveat is you must have that gamma is less than or equal to the posterior content of the plausible region. Otherwise, with this, when it's greater than, if it's less than or equal to, then this set C is this credible region is contained in the plausible region. They're both relative belief regions, right? But if it's bigger, then it's outside the plausible region. And when it contains points that are outside the plausible region. And what does that mean? That means in your so-called credible region, you're including values that have evidence against them. I don't think that makes sense. And it violates our notion, or my notion at least, that evidence in the data must drive all our inferences. Now, it turns out there's a very nice connection between relative belief and frequentism, a kind of a unification of the two. And that comes from the following fact. Bayesian inference generally does not address the reliability of the inferences. I can't recall reading a paper where people were concerned with the reliability. Certainly posterior probabilities do not measure the reliability of the inferences, okay? But that's what frequentism does. And I ask you for the hypothesis testing problem, I pose the following question. Would you believe the result of a Bayesian, you want to test a hypothesis, H naught. And I could show, one could show that before you collected the data, you're going to collect a certain amount of data. And one could show that with a model in the prior that you've chosen, that the prior probability of getting evidence in favor of the null hypothesis was virtually 1. Would you believe the results of that experiment where the experimenter or analyst reported, oh, I found evidence in favor of the null hypothesis? Would you believe it? I wouldn't. I think one has to look at questions like that and determine how reliable is the analysis that's being done, right? And the Jeffreys-Lindley paradox, this is a well-known paradox in Bayesian statistics. Uh, and it answers this question, right? This issue resolves the paradox in essence. So it's just a location normal, and I have a conjugate normal prior. Okay, I'm assuming variance is known. And I want to assess the hypothesis that theta is equal to theta naught. It doesn't matter what prior I use here, but the key feature of the prior is this variance here and what happens to it, right? So I get the Z statistic, and let's suppose it's equal to 5. So what we know, this is the 5 standard deviations of physics, so we know the p-value is equal to this 5.733031 times 10 to the minus 7, right? And so from the frequentist point of view, we've got categorical evidence against the null hypothesis. But what happens when tau naught squared goes to infinity? So you're going to be non-informative. That's what usually people interpret non-informativity to mean. Basically, that the prior is quite diffuse. Well, it turns out the relative belief ratio, which by the way is equal to the Bayes factor here. Why? Because of that previous result. The null hypothesis consists of a singleton value, theta naught. And there's only one conditional probability distribution of a singleton value, right? The distribution degenerate at that value. So the relative belief ratio from that result and the Bayes factor are equal. What happens as tau naught squared goes to infinity? They go to infinity. So in other words, if I take tau naught squared big enough, I'm non-informative, very, very, very non-informative. I'm going to get evidence in favor of the null hypothesis, completely contradicting what happened with the p-value. Now, if I compute the strength, it goes to the p-value. It turns out as tau naught squared goes to infinity. I'm sorry it got cut off there. I'll fix it on the slides that I put up on the website. So that's a partial resolution of the problem. So bias is the issue here. So how do we compute the bias? Well, there's 2 error probabilities. I calculate the bias against psi naught by computing, well, what's the probability that I don't get evidence in favor of psi naught when it's true? I call that bias against. If that's big, then I got a problem, right? Because that means that I'm not going to find evidence in favor of it when it's true. High prior probability. And it turns out, by the way, that this is, thinking about evidence and belief, one shouldn't confound the two because it turns out that biases work somewhat differently than belief. When the prior is very concentrated, I get bias against. Now you would think, well, I'm biasing things in favor, aren't I, when I concentrate the prior? No, because it becomes harder for the posterior to rise up, to get bigger than the prior when I have a concentrated prior. Okay, and similarly for the bias in favor, that's computed by what's the prior probability over the values of psi, a false value of psi, which is meaningfully false, right? Further than delta away from psi naught, that I don't get evidence against psi naught when it's meaningfully false, okay? And then you want these to be small, and they can be controlled. They can be controlled a priori. How? By sample size. And if you look at the Jeffreys-Lindley paradox, well, the bias, as you let tau naught squared go to 0, the prior becomes more and more diffuse. Indeed, the bias against goes to 0, and the bias in favor goes to 1. So by having a very diffuse prior, you see, when you make the prior more diffuse, it becomes easier for the posterior to go up, right, over the prior, be higher than the prior. And that's why evidence and belief work somewhat differently. So you can't fix this issue by choice of prior, because when you choose a prior to make one bias small, the other bias goes up. It's kind of a seesaw effect. The resolution of it is to fix tau naught. Okay, you want to be diffuse, decide how diffuse you want to be, and then make sure you choose the sample size large enough to make these biases small. That's the resolution. For E, all we do is we take the the estimation problem, we take the average bias. We don't have a specific value of psi, so we just add for bias against, we just average with respect to the prior, the bias against, right? And similarly, we average for bias in favor, we average the bias in favor. I guess that's the next slide. But anyway, an interesting fact here is that typically, what is the bias against? We can also, for estimation, it turns out it's 1 minus the prior probability that the true value of psi is in the plausible region. Okay, it's a coverage probability, Bayesian coverage probability. And in fact, usually, all the examples that I've looked at, there's a value, which you take this thing inside here, there's a maximum value, call it gamma. And that implies that the repeated sampling with respect to the model that we get by integrating out the nuisance parameters, that's a confidence interval with respect to confidence region with respect to that model. Its coverage probability is at least gamma for every psi. And as I said, for the bias in favor, we do the same thing. And this is about the coverage probability for the implausible region, right? The implausible region is a set of all values. So we have a false value. What's the probability the false value is not in the set of values which have evidence against them? That's the implausible region. You don't have to go over the supremum over all psi's here, because typically it's achieved when the distance is exactly delta. Now, these bias calculations solve a problem raised in a paper by Mandelkern, setting confidence intervals for bounded parameters. And it's addressed in this paper, and you can find it. It's an open access in my website, right? And basically the problem is this. This arises in physics, okay? So you have a sample from a normal with unknown mean, known variance. And you know that the mean is in some interval. You know it. For them, it's neutrinos, the mass of a neutrino. And the mass of a neutrino is not negative. It's at least 0 or bigger, right? So L0 would be 0, and mu naught would be some upper, U naught would be some upper bound. So one thing, how to get a confidence interval in this context, that's the problem being raised by Mandelkern. And one thing you could do is just take the usual confidence interval and truncate it. But the problem is that interval is too short. It doesn't really tell us the accuracy of the estimate. We're going to estimate by, let's say, the sample average. It's not a meaningful, it has the right coverage probability, but the length of the interval isn't giving us a fair assessment of the accuracy of the estimate, right? In Bayesian inference, we can solve that problem. At least we can solve it from the view of posterior inferences by just taking a prior that's concentrated in the interval from L0 to mu0. So here's a possibility. I'll take a normal prior conditioned to the interval from L0 to mu0. And what I've outlined here is an elicitation procedure for how to specify a mu naught and a tau naught for such a conditioned prior. And I'm not going to go through it here because I'm getting close to my time, right? Got a few more minutes. It's just a conditional normal, right? And then I choose a subinterval that will contain the true value with probability at least 0.99. I call that virtual certainty. It could be 0.995 if you like. This is what Jacob Bernoulli in the first paper on probability called moral certainty. You know something with very high probability is true, right? Something is true with very high probability. So for example, if I take L0, mu0 to be 0.10, and L1, mu1 to be 0.5 to 0.95, mu0 to be 0.5, halfway in between here, and gamma equals to 0.99, I get values for mu naught and tau naught. That's how I elicit the prior. And here I've plotted for different sample sizes what happens to the bias against. This is a plot of the bias against as a function of mu, right? I'm going fast, I apologize for that, but I don't want to go over time. So here's the bias against. You can see for small sample sizes, it's small already. For a sample size 10, the bias against the hypothesis that mu true is equal to 4 is 0.047. So bias against is well controlled. And here's the confidence. Think of a plausible interval. And the plausible interval does not contain values of 0, less than 0, because of the prior, right? It's a confidence, and it is a frequentist confidence interval. These are average confidences I get by averaging with respect to the prior, but these are exact frequentist confidences. I get 0.955 at sample size of 10. So this solves a Mandelkern's problem. There's quite a bit of discussion on that paper too by various frequentists, etc., and they don't really have a good solution to the problem. Bias in favor is more serious of a problem. Here I plotted, there's two aspects to it. There's sample size and there's delta. And you got to be careful about the delta because if you choose it too small, you're going to have the bias in favor is going to be, you're going to need huge sample sizes to get the bias in favor down, right? So I don't have time to really talk too much about that, but here are some of the biases in favor. And you can see if I take delta equal to 0.5, half a centimeter, it's not too bad. But I really have to go up to almost 100, over 50, right, to get small biases. If I take delta to be, well, that's bias in favor for the null hypothesis, but and similarly for estimation, I guess. I've done something wrong there in that table. I'll have to fix it. Sorry about that. And the nice thing is that these biases, they only really depend on the principle of evidence. Any validative measure of evidence can be used. You'll get the same bias measurements. So it's not dependent on using the relative belief ratio. And these are playing similar roles to size and power as in frequentists, right there. And then sometimes they're actually even frequentist probabilities. But they are always they're frequentists with respect to the prior, right? So it's different though. We're not setting an alpha and trying to find a statistical procedure that will find an error probability for bias against of alpha. We're actually choosing the sample size. We might set an alpha and then find the sample size that gives us error. No greater than bias against, less than or equal to alpha, right? And I would assert that these biases should always be computed. Their error probability should always be computed as part of the Bayesian analysis, as they tell us about the reliability of our inferences. And overall, basically what we get is kind of a unification between Bayes and frequentism because Bayesian inference is Bayesian, okay? Because that tells us how to characterize statistical evidence, but so far, at least, frequentism has failed to do, in my opinion, properly. But when we come to assess the reliability of the inferences derived from the evidence, that's frequentist. And I think that is correct. And that's a form of unity between the two apparently opposing viewpoints. So lecture 1, I outline the history of a search for the definition of statistical evidence, which was not successful so far in frequentism. Maybe one day it will be. I can't say that it won't. Lecture 2, as soon as we introduce the prior, and this is why I'm a Bayesian, I get a clear definition of statistical evidence. There are questions, how to choose models and priors. Well, for priors, I know elicitation. For models, that's a little bit unclear to me still. How do we advise people how to choose models? Now, both models and priors are falsifiable, right? We can falsify a prior by a model by model checking, falsify a prior by checking for prior data conflict, and there's papers on my website about that. Bias calculations are necessary, are essentially frequentist, and they form an essential link. So if I had one final comment, I would say that my hope for the future is that we collectively recognize how essential the concept of statistical evidence is, and also the associated reasoning process, because I think it clears up a lot of problems for statistics. Of course, that's Mike Evans' opinion, and Happy New Year to all, and thank you very much again.